Sorry, I'm here to present a joint work between the Piper Lab at Purdue University and Politecnico di Milano on reliability map estimation for CNN-based camera model attribution. So let me start by telling what's camera model attribution. Basically, when we talk about it, it's just detecting which camera model has been used to acquire an image just by looking at the pixel information on it. We don't look at JPEG headers. We don't look at text with information, just the pixel distributions on the image. Extensive forensic literature has showed that CNNs can do this even very well on small image patches. We are talking about 64 by 64 image patches, which is relatively small compared to the full resolution images that we have nowadays. But the problem is when we work with these small patches, even that we can ensure that we are not learning scene information, in some cases they may not be informative enough to learn the camera model problem. So the solution we propose in this case is a CNN-based solution that can be easily integrated in the current CNN architectures for camera models and allows to be jointly trained to leverage transfer learning strategies and properties. RME indicates which portion of the images have reliable camera traces, such as PRNU or the Bayer filter that has been used for the color interpolation. And it can also be used to drive tampering and localization methods. So basically here is an overview of our proposed approach, where we extend our previously presented on the signal processing letters and electronic imaging BGG-like patch feature extractor, and we extend it with fully connected layers that allow us to predict the reliability of every patch while keeping the computational complexity at a minimum. So to experiment or validate our approach, we started testing multiple architectures and different learning strategies, and we validate them on the Dresden image database. It's a very well-known forensics dataset, openly available, which contains 18 camera models. And we can see after intense testings that the proposed approach leverages both CNN feature learning and capabilities and transfer learning training strategies. To make sure that the CNN-based approach is the most computationally efficient and it performs the best one, we tested against several methodologies, classic supervised methods like boosted forest, logistic regression, and other kind of testings. And as you can see on the left side of the lower figure, our proposed approach is the best one in this case. So just to give you a sense of the kind of results that we can obtain for the relativity map estimation, here are some of the images on the test set, and we apply our method to them. And I think the main takeaway here that you need to learn is that even if some of the patches are partially influenced by the underlying content on all of them, we can see that the reliability traces are fairly independent of it, which is kind to be expected because extensive forensic literature has shown that the features that the CNN learns in these cases are basically photo response non-uniformities, coming basically from the silicon embeddings, the time when the manufacturer creates silicon wafers. And that's what our experimental results have shown. And also here, just to make sure that everything is working well, we present you the confusion matrix for the 18 camera models. And you can see on the left side, without the relativity map estimation, there's several confusion between models, which is kind of expected. One of the most interesting ones is in the lower right corner, where we have confusion, I think, between some Canon models. This is also interesting because it allows us to show that even when some brands can try to sell you like more expensive models, if you look at the sensor level, you can see that they are equivalent. So maybe the performance is only on the software side, but when it comes to compare the images on the pixel level, you cannot see the difference. Then when we applied the relativity map estimation, we can see that this confusion basically disappears. In some models, it's still consistent because, as we have mentioned before, it's on the silicon level, so we cannot do anything to differentiate between them. But we can increase the accuracy on the camera model attribution by more than 8%. So the original accuracy on the state of the art was around 87%. And with our method, we extended to 95%. And this is on a patch level base, which is fairly good. So with this, I want to end my talk, and I welcome you to the poster 2B13, and let's have further